So last time we started talking about statistics, and the main emphasis in class, at the end of class, was what a statistic is. A statistic for us is a theoretical idea, though we do use calculating technology, calculators, spreadsheets, Mathematica, to do calculations, to see, observe values of statistics. But in general, it's a function, call it in the abstract, h of x1, comma, x2, comma, dot, dot, dot through xn of a random sample. X1 through xn represents a random sample of size n from some population. And what I emphasized the other day is what the population is really a distributions. Yes, you could think more intuitively in terms of populations being people or things or companies. But in the abstract, for the purposes of our class, to do the theory that we need to do to apply the statistics, we need to think of the population as essentially a distribution, meaning a random variable, really. And that random variable has everything that comes with it that we have always talked about to this point. If it's discrete, it's got a probability mass function, PMF. It's got a cumulative distribution function. We can find its mean, its variance, its standard deviation. If it's continuous, it's got a probability density function, PDF, that we find probabilities with by integration. We can find the other things, second moments, variances, standard deviations, etc. But in reality, when you do statistics, you often don't know what the population is, whether it's a population of people or objects or whatever, or whether it's a population as a distribution. You may not know exactly what the distribution is. You might have a guess. You might have a model for the distribution. Maybe you think the distribution is normal. That's one of the most common things to assume, is that it's some normal distribution. And based on that assumption, you then gather data and see, well, how well it fits that model. And you also see, assuming it does fit the model, can you reach conclusions? Such conclusions are called inferences. We want to make inferences, but the goal is to create models, to do what's called inferential statistics. There's two main branches of statistics. There's descriptive statistics, which is what chapter 6 is titled, descriptive statistics. That's what most people think of when they hear the word statistics. It describes situations with data. Maybe it's a sports situation, maybe it's a company or a bunch of companies and their revenue, their profits, their market valuation, that kind of thing. Data, graphs, that's what people think of when they hear the word statistics. But we're mostly going to do inferential statistics. That's a harder subject. That's where we're using these models to make predictions. With inferential statistics, we're making predictions about the population. And if you are thinking more intuitively about the population as being, for example, a population of people, I could, yes, go ahead and take a sample, a random sample of people, students here at Bethel, measure all their heights, find the average height for that sample, do an actual calculation, add up all those numbers and divide by how many I have, get a certain number, I don't know, 5'8", and say that's my best estimate for the true unknown average value of the population. I could literally think of population as being people. But I also, again, could think of the population as being a distribution, like a normal distribution. And I'd be assuming that all your heights are normally distributed and trying to estimate that unknown mean. Now, there are some approximations going on here, right? For one thing, there's an approximation when I'm actually doing my measurements. For another thing, there's approximations in that model and assuming a normal model. And really, when you're assuming a normal model, you're kind of assuming an infinite population. But there's only finitely many of you, even among all Bethel students. There's only finitely many of you. So is really a normal model like that appropriate? The basic idea is that it's still a good approximation. We don't worry about some subtleties like that unless we need to. The main way we do inferential statistics in this class is twofold, with something called confidence intervals, and something called hypothesis testing. With confidence intervals, you're trying to estimate a population parameter, meaning like a population mean or a population standard deviation. You're trying to estimate them. And you're also trying to acknowledge that using just one number, like say I get an average of 5'8", using that one number is not really ideal, because in all likelihood it's wrong, right? Because I just took a sample. It would be good to know how far off it's likely to be. It'd be good to have a little bit of cushion. That's the basic idea of a confidence interval. Instead of a one number, 1 point estimate, you widen your interval to your estimate to an interval estimate. I think I'm pretty confident that the true average height of the population is between 5'7" and 5'9". I took my point estimate at 5'8" and widened it to an interval estimate from 5'7" to 5'9". But even then, there's still no guarantee that it's right. The true average could be 5'6" or 5'6½". Not in that interval even. How do you deal with that? You have to assign what's called a level of confidence to it. I'm 90% confident, or 95% confident, or 99% confident. In reality, the only way you get to 100% confidence is if you go extreme and say the interval is the entire real number line, or I guess for heights, all numbers greater than or equal to 0. But wait a minute, that's not very useful. So it's always a balancing game between accuracy and certainty, you might say. Hypothesis testing, you have hypotheses, you think reality is a certain way, and you're wondering based on the data if the data tends to confirm your thoughts about reality or reject your thoughts about reality and say reality is different, okay? Say, for example, with regard to heights. Maybe I have a hypothesis that people at Bethel are really tall and the average height of everybody is like 6 foot or higher. But somebody else thinks, no way. I'm going to gather data and prove you wrong. And you gather data and you find a sample mean of 5'10", less than 6 feet. Is the 6 foot or higher hypothesis disproved? It's some evidence against it, but is it really good evidence? Is it strong evidence? The phrase is it statistically significant evidence? That's not so clear. We have to use our probability models to figure out. We have to figure out probabilities of things to help us decide whether it's strong evidence or not against the hypothesis that the mean is 6 foot or larger. All this stuff that I'm saying here in a short amount of time right now is going to become more and more of your reality as you get into reading more, doing more homework problems, and we go through more classes here today and next week especially. Chapter 7 is the foundation for everything that follows. Chapter 7 is the hinge point of the entire book. Okay, first 6 chapters are the probability and the descriptive statistics leading to chapter 7, which is the theory that we need to do the statistics that comes later on. It's the hinge. Please stop me if I can clarify anything. And it is good to pay your best attention that you can. The way you think about math and statistics is everything. Well, maybe I shouldn't say everything. A big portion of everything. It maybe doesn't completely help you solve the problems you need to solve, but it's a big part of problem solving, is how you think about it. I'm going to emphasize that over and over and over again. Our main example that we talked about with the statistics last time was the sample mean. So statistics, not statics, statistics, examples. The most important example is the sample mean. Emphasis not just on the word mean, but also the word sample. That's very important. If you just say the word mean, there's lots of things you could mean. And they all mean different things, but they're related. Capital X bar. When we're thinking about it in the abstract, use a capital letter to emphasize this is a random variable. It's not any old random variable. It's a special random variable. It's a statistic. It's a function of a random sample. And remember what a random sample is. It's a finite collection of independent and identically distributed random variables. Independent, technical hypothesis based on the idea of independence in chapter 5. Remember independence of X and Y back in chapter 5? X and Y were independent if and only if their joint PDF was the product of their marginal PDFs. That was the definition of independence. It actually generalizes not just to 2 random variables, but to n random variables. The definition of independence really means that the joint PDF for the n-dimensional random variable x1 through xn is the product of the individual marginal PDFs. This is kind of funny. F of x1 through xn equals the product f sub x1 of x1 times f sub x2 of x2, etc., through f sub xn of xn. The subscripts are capital letters. The inputs are lowercase letters. That's what independence means. It's a technical assumption you make. To do the theory, to make the theory a lot easier. If you don't assume independence, the theory is a lot harder. In some circumstances, it might be a better theory. It might be more realistic for modeling reality. But if we're going to do the core theory that we need to do that's easier than the other theory that's about non-independence, we need to make this assumption. Will you ever need to use this fact that this joint density is the product of the marginal densities? Not really, not in this class. We take a more intuitive approach to independence for the most part. If I know the observed value of x1, it doesn't tell me what I would expect to observe for the values of the other ones. Independent. Identically distributed. They have the same distribution. They have the same PDF if they're continuous random variables, for example. We use different subscripts, though. It's wrong to say they're the same random variable. Instead, you say they have the same distribution. But their observed values can be different when you actually carry out the experiment. Coming back to the sample mean, it is a statistic. It is a function of the random sample. Add up the capital Xi's and divide by how many there are. It's a chapter 7 fact. A fundamental fact in chapter 7, one of the most fundamental facts in statistics, is that X bar, capital X bar, is an unbiased estimator of the population mean, mu. X bar, the sample mean, is an unbiased estimator of the population mean mu. Okay, gotta get the concepts right. Remember, for us, a population is really a distribution, a random variable that's got a distribution. That distribution has some mean. Well, actually, it is true that some distributions don't have a mean, right? Sometimes the mean is infinite because like the improper integrals diverges. We don't typically like distributions that have an infinite mean. So we're implicitly assuming the mean is finite here, that it exists. And in that situation, this is an unbiased estimator for that unknown number. But what does this mean? What does it mean to be an unbiased estimator? This means, there we go, using the word mean again. This means that the expected value of X bar equals mu. The mean of the mean is the mean. Mu is a number, parameter, if you want to use the word parameter. We've used the word parameter before, right? Whenever we talk about distributions that have names, geometric, binomial, Poisson, gamma, exponential, chi-square, normal, those are the most common ones we've talked about, uniform. Those distributions have parameters associated with them. With a normal, it's mu and sigma squared, the mean and the variance. With gamma, it's alpha and beta. With a binomial, it's n and p. Those are parameters. You're assuming your population has a parameter, a mean that's typically unknown, but you're assuming it exists. X bar is a statistic. It's that. It's a function of the random sample. These are random variables, therefore the entire expression is a random variable. X bar is a random variable. X bar has a PDF and a CDF and a mean. Its expected value is its theoretical mean. We're saying that expected value is the population mean. The mean of the mean is the mean. But each of these means is a different mean. Population mean, number. Sample mean, random variable. Expected value mean, what should I call that? Operator, expected value operator. E of something. It's kind of like a derivative operator, DDX. Take the derivative of something. Take the expected value of something. Expectation. It's a kind of mean. This is going to be more clear, I hope, as we do some simulations here in a few minutes. What's another example of a statistic? I'll just mention one verbally. We talked about the median last time, a couple verbally. Maximum, minimum, those are statistics. Here's a new one that you should have read about. The sample variance. Not written sigma squared. Instead written capital S squared. That's very important that you use an S and not a sigma. And this is a capital S. It's a random variable. But it's also a statistic. So it's a function of the random sample. If I've got a random sample, I can give a formula for this in terms of the random sample. And the formula is this. Here's how it's written in the book. Summation I goes from 1 to n of, in parentheses, capital Xi minus capital X bar squared divided by n minus 1. And that's not a typo. Don't divide by n, divide by n minus 1. I hope, being math and computer science majors for the most part, you realize that with respect to the summation, the n minus 1 is a constant. 1 over n minus 1 could be brought out in front. I also can write the formula this way. As the fraction 1 over n minus 1 times the summation. And I also could kind of write it like I did at first. When I wrote this first one, I'm kind of thinking of adding up all those things. But I also could put the summation in the top of a fraction and put the n minus 1 below the summation. I also could write it like that. Any one of those three ways is fine. Why are we dividing by n minus 1? Why not n? Wouldn't that make more sense? It's actually a little bit of a debate in the statistics community. Some statisticians buck tradition and divide by n instead of n minus 1. From what I can tell, talking with various statisticians and reading stats books, it seems that most statisticians agree you should divide by n minus 1. But why? Well, I mean, we are kind of taking an average here, aren't we? And this average should be related to the variability of the random sample. Doesn't this make some sense? I mean, we're adding up squared deviations from the mean. If the xi's, if the observed values of the xi's tend to be close to the sample mean, x bar, the observed value, these differences will be close to 0. And if they're really close to 0, when you square them, they'll get even closer to 0. And you'll divide by n minus 1, you'll get a small number. You'll get a small observed sample variance. Variances are supposed to be measures of variability. On the other hand, if all the xi's tend to be far away from the mean, some higher than the mean, some lower than the mean, these differences will tend to be large in absolute value, some positive, some negative. You square them, if they're further away from 1 than further away from 0 than 1 unit, the distance will get even further when you square, though you get a bunch of positive quantities, possibly very large numbers that you add up to get a large sum, divide by n minus 1. Yeah, that will make it smaller, but maybe not a ton smaller if they're really large numbers. That's a lot of variability. So it's intuitive that this should be some kind of measure of variability, but why divide by n minus 1 instead of n? Here's the reason. And this is chapter 7 as well. These formulas are in chapter 6, but these facts about being unbiased are in chapter 7. Chapter 7, S squared, the sample mean, is an unbiased estimator of what? Excuse me. X bar was an unbiased estimator of mu. And that's what that means right there. And we'll talk about what this means intuitively here in a few minutes with simulation. S squared, was that an unbiased estimator of mu as well? Would that make sense? Probably not. What do you think it's an unbiased estimator for? Sigma squared. Yeah. The sample variance is an unbiased estimator of the population variance. Population variances are not computed, at least when the random variable is continuous, with a summation. They're computed by doing integrals. Yeah, they're computed with a summation when it's a discrete random variable, but it's not this summation. It's not that. You got to calculate first and second moments, remember, and use the shortcut formula. You are calculating moments, you are doing summations, but it's not that summation. This is an unbiased estimator of sigma squared. This means the expected value of S squared is sigma squared. And you could say this, the mean of the variance is the variance. Or to be a bit more careful about it, the mean of the sample variance is the population variance. Why? Well, I guess you could ask why this is true as well. Actually, let's figure out why this one's true first. Why is the expected value of X bar equal to mu? It's one of those things that seems really mysterious when you first look at it. But if you follow your nose through the formulas and use properties of expected value and assumptions we're making, it's really actually pretty easy to prove. What's the most natural next step to do? Well, just, I guess, use the formula for X bar. 1 over n times the summation, I goes from 1 to n of xi. And we know from chapter 3, and it was also true in chapter 4 with continuous random variables, that the expected value operator is linear. It's like a linear transformation. Is it really? Sort of. Those are not vectors in the usual sense. But it's kind of like a linear transformation from linear algebra. You can factor out the constants like that. Oops. 1 over n times the expected value of the summation. And then, yeah, the expected value of the summation is the sum of the expected values. I can bring the summation sign out. I mean, it's as if you're taking a derivative of something. It's like you're taking a derivative of a constant times the sum of functions. You can factor out the constant and add the derivatives of the functions. Kind of like that. Obviously not the exact same thing. But this just begs a question, where do I go from here? Anybody have a bright idea of where to go from here? Those x's have the same distribution. That distribution has mean mu. How in the world am I going to get mu into this equation that I'm trying to prove? Go ahead, Michael.
Same distribution. Expected value of x bar should be the same expected value.
Yeah, each one of these is a mu. No matter what I is. I can be 1, 2, 3 through n. It doesn't matter. Because each xi, x1, x2 through xn, they all have the same distribution. They all have the same mean as random variables. So I'm just adding up a bunch of mu's. How many of them? N of them. The n's cancel, and I'm left with mu. Done. That's all there is to it. This may seem insignificant, but it's actually everything. Okay, not everything, but a large amount of things. This is fundamental in statistics right here. This fundamental fact based on properties of expected value. I guess the same kind of thing should be true up here. I should be able to prove that. Guess what? That's a lot harder to prove. The book does do it. It's near the back in an appendix. If you want to look at it, I'll show you here on the screen. It's on page 782 and 783. Here's the theorem itself at the bottom. Let S squared be the sample variance based on a random sample of size n from a distribution with mean, mu, and variance sigma squared. S squared is an unbiased estimator for sigma squared. Proof. By definition. Oh, is that it? No, the proof goes, oops, the proof goes on to the next page. It takes up most of the next page. Yeah. It starts kind of promising. I'm dividing by n minus 1. I can factor out a 1 over n minus 1. But then after that, it's like, yeah. Actually, each step is not too hard to follow. You can verify each step. Believing you could do it yourself, though, is another thing. It's hard to believe in looking at that you could come up with that on your own. I would be hesitant about my own ability to come up with this on my own. But in the end, each of these xi's is a random sample from the same distribution with the same variance. Remember the definition of the variance? It's not the computational formula, that's the definition of the variance. Expected value of x minus mu quantity squared. That's the definition of the variance of x. Each one equals sigma squared. Replace all these terms with sigma squared like that and simplify it, and suddenly you get a sigma squared at the end, like magic. And the proof is complete. So I'm happy, and you should be happy, that somebody figured all this out. But it still doesn't really provide much insight into why we divide by n minus 1 instead of n, other than to say, oh, that's just how it works out at the end. Can we get into any insight into why they divide by n minus 1? Well, to some degree, but to some degree, it's just this, the details of that calculation. That is the way that works out. Well, what does it mean? And how do you interpret this unbiased idea intuitively? That's with simulation. Let's do some simulation now. First, let's simulate with a spreadsheet. So what I'm about to do, I'm trying to verify with simulation that x bar is unbiased for mu and s squared is unbiased for sigma squared. Actually, I'm not going to be able to completely do this on the spreadsheet. I'm going to need Mathematica as well to verify something. And then we'll also do a simulation with Mathematica. Let's say my population is a distribution that's uniform, continuous uniform distribution on the interval from 0 to 10, say. So we're talking, if symbolically, we're about to simulate a U010 distribution. Actually, maybe we should do some hand calculations first. So when I say U010, I mean a continuous uniform distribution on the interval from 0 to 10. So the PDF, little f of x, is going to be, remember, we want the area to be 1. Uniform distribution, the graph is a horizontal line above the domain where it's positive, 0 to 10. That's got a length of 10, so it's got to be 1/10 to make the area 1. If x is between 0 and 10, and 0 otherwise, I could also find the CDF. I won't bother. What's the mean? Well, it should be 5, right? Halfway between 0 and 10. Is it? Integrate x times f of x from 0 to 10. I am integrating 1/10 x from 0 to 10. It's going to give me 1/20th x squared from 0 to 10. That's 100 over 20 is 5, just like you would expect. That's a joke. Expect. Second moment, you're going to end up integrating 1/10 x squared to get 1/30th x cubed from 0 to 10. 10 cubed is 1,000. 1,000 over 30, which is the same as 100 over 3, which is 33.3 repeating. That's not sigma squared, though, right? Sigma squared, the second moment, minus the square of the first moment. 100 over 3 minus 5 squared. 100 over 3 minus 75 over 3. Right? Yeah. 25 over 3. Or what would that be? 8.3 repeating. That's the population variance. Population standard deviation would be the square root of that, which would be a little less than 3. So we're trying to do simulations that estimate these parameters, 5 and 8.3 repeating, are what we're about to try to estimate. First with the spreadsheet. If I type equals rand like that with parentheses, it gives me a random number between 0 and 1. If I re-enter it by copying and pasting, it gives me a new number. Bunch of random numbers between 0 and 10. If instead I do equals 10 times rand, that'll give me a random number between 0 and 10. If I copy and paste this down to say get a sample of size 25, there's a bunch of observed values of x. You could call it a random sample. Observed values of x1 through x25. You could label them with lowercase x's, little x1 through little x25, because these are observed values. What's their mean? Type equals average. A1 colon A25. Now, realize, again, the spreadsheet is set up in such a way that every time I do a copy and paste, or every time I enter a formula like this, the numbers actually get updated. It's not a big deal. You can do a paste special to paste the particular values you're looking at for all time, but you don't have to. It doesn't matter that they change every time. So I'll enter this, they'll change. What should their average be close to? Probably 5, yeah? Well, not too close. Let's try it again. That's a bit closer. Do it again. That's pretty close. Okay. Typically, they're pretty close to 5. Sometimes further away than you might hope for. If I kept doing this copying and pasting that I'm doing over and over again to keep changing the simulation every time, about half the time the numbers will be bigger than 5, and about half the time they'll be smaller than 5. That is a simulation illustrating X bars unbiased for mu. Now, I'm not literally counting how often they're bigger than 5 and how often they're less than 5. But that's the intuitive idea. I could also do equals, actually, I usually do standard deviation. Bar, does that do a sample variance or a population variance? I think I better do equals STDEV for standard deviation and square it instead. That's what I'm more used to doing. Just to play it safe. As I start typing equals STDEV, notice more than one option comes up. A plain STDEV, STDEVA, STDEVP, dot P, dot S, PA. I've never used any of those other ones. Maybe I've used the P to illustrate a population variance ultimately. Just do equals STDEV. But then square it to get a variance. If I copy and paste to do new simulations, about half of these numbers should be smaller than 8.33, and about half should be bigger than 8.33. This one's smaller, 6.24977. Copy and paste. Did it work? Okay, that one's smaller. That one's close to the 8.3 repeating, but still smaller. That one's bigger. That one's smaller, bigger, smaller, slightly smaller, 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 bigger. We could actually do even more to illustrate this. We could copy and paste this entire column. Oh, to the right to do a bunch of random samples of size 25. How many should I do? Maybe I should do 25 of them. I guess I got to go to column Y, right? Or should we do 26, column Z, 26 letters in the alphabet? And for each one of those, compute the mean and the variance. Copy and paste the formulas over. And then with each of those lines, the one line for the mean and the one line for the variance, I could make a histogram, which you read about in the past couple days. Insert chart. Not that chart. Suggested histogram. That's a histogram for the means. It's not perfectly symmetric. It would be more symmetric if my sample size were large enough. I picked n as 25. I got 26 samples of size 25 here. And it's making a histogram. If n were bigger than 25 by a lot, like 100 or 1,000, the histogram would be closer to looking like a normal curve, actually. But it is centered, you can see, pretty close to 5. I could even take the mean of these means. I could type equals, and well, actually, if I re-enter stuff, it'll change the graph as well. If I go equals average, what would it be? A27 through Z27, average 26 means, find a mean of a mean. It should be really close to 5. I'm going to enter this, the graph will change because the numbers will change. Not very symmetric at all. But yeah, this number is very close to 5 now. And okay, if I do a copy and paste update things, we can see different simulations. Wow, that's a weird graph. But all those numbers are pretty close to 5. That one's pretty symmetric. Looks kind of like a normal distribution. And if I do something similar with the variances, insert chart, histogram. Did it just copy over the other one? I'm not sure if it copied over the other gram or what, the other one. Yeah, okay, there are 2 here. Okay, this one should be centered close to 5, and it is. This one should be centered at 8.3. Yeah, pretty close. This one's for the mean, this one's for the variance. That's good enough for simulation in the spreadsheet, but I do want you to know how to simulate this on Mathematica too. And even calculate parameter values in Mathematica as well. For example, we can confirm the mean of a uniform distribution. Where'd my cursor go? There it is. On the interval from 0 to 10 is 5. And we can confirm the variance (8.3) repeating, what, 25/3? Standard deviation would be the square root of that, 5 over square root of 3. We could also confirm that. And maybe I didn't emphasize this enough, this spreadsheet and Mathematica are using the n-1 formula. the S squared formula for the variance. There's the standard deviation. So that's confirming the theoretical parameter values. Let's also confirm it with simulation. How? Well, let's see. Remember, RandomVariate is how you create random samples. If we want it from a uniform distribution, we could put that in here. If I just do one of them, it just gives me one number, but every time I do it, it gives me another number. If I put a comma, say 25 here, it gives me 25 numbers from that distribution. And that data is going to have a mean close to 5 in general. If I go extreme and go 10,000 data points, put a semicolon to suppress the output, this mean should be really close to 5. Okay, 100,000. Really close to 5. We don't want to see the output for this, right? So I put a semicolon there to suppress the output, but I want to see it. Or maybe you do want to see it. We could use, we could say data sets is applying RandomVariate over and over again, like 26 times, like I did in the spreadsheet. Oops. Now I got a bunch of I got 26 random samples of size 25. I could make a histogram of that. Oh, that's pretty. I didn't expect that though. Oh, it's making a bunch of histograms. Okay. There's one of them. That's not a very fine histogram though. Let's do a bigger sample size. Oh, let's go ahead and do 10,000, but suppress output. Oops. Guess I gotta put 10,000 there. Looks uniform. Doesn't look like a normal curve because, okay, yeah, okay. I need to do the mean of those things. Means. The syntax for calculating the mean of each data set would be to map the mean function over the data set's function, I think. It's really means that I want to graph here. This is kind of like the spreadsheet output graph. If I do more than 26 samples of size 25, I guess they're samples of size 10,000. Let's do 100 of them instead of 26. It is looking a bit more like a normal curve that way. And the sample size was pretty large, 10,000. So that's to be expected, actually. But it's centered on 5. If I do the same kind of thing for the variances, instead of mapping the mean over the data sets, I map the variance function over the data sets and call them variances. I get a bunch of variances that I can make a histogram for as well. And it looks like a normal curve, actually, centered at 8.33. The expected value of the means, the expected value of X bar is mu. You graph a bunch of these means, it should give you a histogram that looks like it's centered very close to 5. Now, it's still simulation, so it's not going to be perfect, but it's pretty close. And with the variances, it's centered close to 8.33. And if instead I had divided by n instead of n minus 1, it would not be centered at 8.33. It's not a proof, but it helps you believe it. Mathematica is dividing by n minus 1 here. That's the default. And the spreadsheet function equals standard deviation equals STDEV. The assumption is to divide by n minus 1. That's the default. If you put a p on the end of it, population, then it divides by n. On your calculator, when you do this kind of stuff with data, I'm not bucking most statisticians here. I want you to use the n minus 1 version. So when you've got data on the calculator, I've got a data set in there right now. I guess it's from the other day. And I go to my stat menu to calculate one variable stats of that list. The mean is 2.3083 repeating. What standard deviation should I use? Use the S one. Don't use sigma. Never, ever, ever, ever use sigma in our class. Now, if you go on the job, you might decide I'm going to buck Dr. Kinney and I'm going to use sigma. But maybe your boss won't like it. Not because they like me, they even know about me, but right. Your boss might say, no, use the sample standard deviation, not the population one. Divide by n minus 1, don't divide by n. Notice this one's slightly bigger than this one. Use the S. Always use the S. You never, ever use the sigma. Never, ever, 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 ever in this class. Always use the S. This still begs other questions. So I said S squared, the population variance, is an unbiased estimator for sigma squared, the population. Said that wrong. S squared, the sample variance, is an unbiased estimator for sigma squared, the population variance. Does that mean S is an unbiased estimator for sigma? Unfortunately, no. Unfortunately, and this really is, I guess, unfortunate. Unfortunately, S, the sample standard deviation, square root of the sample variance, is not an unbiased estimator for sigma, the population standard deviation. Not. In other words, the expected value of S does not equal sigma. Oh, how terrible. Well, we live with it. If you divide it by n instead of n minus 1, it still would not be unbiased. I'm calling it not unbiased. Does that mean I should call it biased? Sure, you can. I.e., it's biased. But even if we divide it by n, it would still be biased. So we still don't divide by n. We're happy to live with the fact that the sample variance is unbiased for the population variance. We're happy about that. We're not so happy about this, but we live with it. That's kind of why mathematical statisticians, theoretical statisticians, they prefer thinking about variances than standard deviations, right? Who wants to deal with square roots and who wants to deal with this? We'd prefer not to. I mean, if we have to, we do, but that's why we typically are avoiding talking about standard deviations sometimes. Sometimes we have to do it. Is there a way we could make it something that avoids dividing by n minus 1? Could we create another statistic that avoids that? Well, kind of. But people never do it because it's just not practical. One way you could avoid dividing by n minus 1 and divide by n instead is to use the population mean mu here instead of x bar. However, that's problematic. Why would that be problematic? To use a mu instead of an x bar up there. Think practically, like you're doing a study, trying to do inferential statistics. What would be the problem with trying to use mu there instead of X bar? Yeah, mu is unknown. How can you use it if you don't know it? You're trying to estimate it. That's the point. You're trying to estimate mu. You use X bar to estimate it, but then if you use X bar in this formula, then you have to divide by n-1 to make this unbiased. Statisticians say we have lost a degree of freedom when you replace mu with X bar. n-1 in this context is sometimes called the degrees of freedom. We've used that phrase before with chi-square random variables. Still doesn't give you a ton of intuition. You either got to trust the proof in the back of the book or trust the simulations. There's just no other way around it. But still doesn't give you a ton of intuition. But we trust it. Here, there is a computational formula for S squared that you also could use to calculate the observed value of S squared. And by the way, the observed value of S squared, you would use a lowercase s and take its square root to get the observed value of S, the sample standard deviation. Use lowercase then. We're using capital letters in this formula. These are random variables. Shortcut formula, computational formula. To tell you the truth, more useful in days before calculators and computers to use this than it is now. Now it's not really necessary. But you might want to practice it a couple times and see that you get the same answer. I will come back to this near the end of the semester when we talk a little bit about regression. And we talk about something called SS formulas, sum of square formulas. This is related to that. But don't worry about it now. What are some other important facts at the beginning of chapter 7? Let's page to chapter 7 now. Chapter 7 is my favorite chapter. I've said that before. Okay, let's summarize the things in section 7.1. Theorem 7.1.1 is a theorem that I just proved 20 minutes ago. Sample mean X bar is an unbiased estimator for mu. There's the proof. That's the exact same proof I just did 20 minutes ago, or whatever it was. Expected value of X bar equals mu. Actually, there's something that comes before this. There are this list of two things that are desirable properties of a point estimator. Theta hat is an unbiased estimator for theta, and theta hat has small variance for large sample sizes. What's theta? And what's theta hat? This is the admittedly weird notation statisticians use for parameters in general. Theta and theta hat. What? Where are the angles? Doesn't theta have to be an angle? No, of course not. Theta doesn't have to be an angle. We're just so used to theta, it's always being an angle that we look at that and say, where are the angles? It's not an angle. Okay. Theta is the symbol for the general population parameter that statisticians use. Theta could be mu, could be the population mean. It could be sigma squared, the population variance. It could be sigma, the population standard deviation. Could be something else. Could be the population median. For a continuous random variable, the population median would be such that half the area under the curve is to the left and half the area is to the right, right? That's the population median. And for a right skewed distribution like this, the population mean would be further to the right. So there's the population mean mu, here's the population median m for a distribution like this. Could there be the population skewness? You haven't computed any skewness before, but I've mentioned it before. It's related to the third moment of a random variable. There's also kurtosis. I think I mentioned that. Related to the fourth moment of a random variable. And those are descriptive statistics for parameters, you might say, for describing distributions. Theta hat is your general symbol for the estimator of theta. It's very important to say estimator. Sorry that I messed that up there. E-S-T-I-M-A-T-O-R. Don't say population. Don't say estimate of theta. Say estimator. That's very important. An estimate is an observed value of an estimator. I won't usually emphasize the tor that extremely. I should say estimator. An observed value of this, you could call it estimate. But by saying estimator, you're emphasizing it's actually a random variable. Theta is a parameter. I guess I'm writing the word parameter twice there. Theta hat, I should point over there. Theta hat is a random variable. Statistic. Statistics are random variables. Special kind of random variables. Every statistic is a random variable, but not every random variable is a statistic. X bar statistics are functions of random samples. As a function of a random sample, x1 through xn are random variables. X bar itself, the statistic, is a random variable as well. Definition, theta hat is an unbiased estimator for theta if the expected value of theta hat is theta. The mean of theta hat is theta. The mean of the estimator is the parameter you're trying to estimate. You also want it to have small variance for large sample sizes. Theta hat is a random variable, it's got a variance. You want the variance of theta hat to be small if n is large. The sample size is large. That's desirable as well. It's called, basically it's called consistency, or it's a consequence of consistency of an estimator. We don't really emphasize that in this class much, except for one example. An example I'm about to show you, actually. Yeah, let's go ahead and show that to you. What's the variance of X bar? It's sigma squared, the population variance, divided by n, the sample size. And yeah, that's small when n is large. The variance of the mean is not the variance of the population. It's the variance of the population divided by n, the sample size. Is that hard to prove? Based on rules of variance, it's similar to the proof that we did in class 25 minutes ago. It's not too hard, actually. It's a similar kind of proof. Does it make intuitive sense that you divide by n? The bigger n, the smaller the variance of X bar is? Yeah, actually, that makes some intuitive sense. If your sample size is really large, and you compute the variance of the mean, meaning you do many, many sample sizes of that same large value of n, like pretend n is 10,000 or something, you would expect the values of X bar to be close together, like close to 5 for our uniform example. You would expect a small variance. On the other hand, if our sample was small, sample size was small, like 2, we could get pretty large variances from our samples. And our sample means can vary widely. They're not necessarily all close to 5. I mean, if my sample size is 2, there are a pretty decent chance that both of my numbers could be close to 10, for example. And then X bar itself would be close to 10 instead of 5. Having larger sample sizes tends to average out extremes, outliers. They go away by averaging. I'm picking a random sample of Bethel students to measure heights of the first person I happen to pick as a basketball player. The center on the team, who's, I don't know, 6'10". Who's the center on Bethel's men's basketball team? Nobody knows. I don't know. 6'10". Oh, if I use a sample size 1, I don't get a very good estimate. But the next person I pick happens to be 4'7". The extremes averaged out to close to 6 feet, say. This is a definition of standard error. The standard deviation of X bar is this, the square root of the variance. It's called the standard error of the mean. And this last theorem was about being unbiased. In our last 8 minutes, take another breath. I would like to start the next section and do a basic example of the next section. The next section's got 2 topics, the method of moments and the method of maximum likelihood. They're both kind of confusing topics, though I will say maximum likelihood is a lot harder than method of moments. So we do method of moments first. Let's do a simple example of method of moments. Let's in fact go through the book's example here. What's the situation? A forester plants 5 rows of 20 pine seedlings, little trees, each row to serve as an eventual windbreak. Soil and wind conditions to which the seedlings are subjected to are identical. Variable being studied is X, the number of seedlings per row that survived the first winter. So we're dealing with a random sample of size 5 because there's 5 rows, right? 5 rows, there's the 5. Each row has 20 trees, and P, the probability that a tree survives the first winter, is unknown. Okay, yeah. The goal of the study is to estimate the probability that a tree survives the first winter as a seed. Something important to study in Minnesota, right? Will it survive the winter? P is the population parameter we're trying to estimate, based on a sample. In fact, 5 samples of size 20. Now, could you call it a sample of size 100? Yeah, you could. But that's just not the way we're conceptualizing. For the purposes of illustration, I guess. What are we after? In this problem, what we're after is we're after a theoretical estimator for P. P is like the theta. And we'd like to come up with a theta hat that we're going to call P hat. Without just showing you what the book does, let me just describe it on my own here. So, introduction to the method of moments. And I'm going to give you at least 1 or 2 problems where you try to use this method. What you do in this kind of situation to estimate a population parameter for a parameterized distribution, in this case, a binomial distribution with n equals 20 and P is unknown, is you write down, first of all, an equation you already know, that the expected value of X in this case is n times P, which in this case is 20 times P. That's a fact from chapter 3. We know that. The expected value of the binomial random variable is the number of trials times the probability of success on each trial. The trials are the trees, effectively. Does this tree survive or not? With the method of moments, what we're trying to come up again with is a theoretical estimator for P. What you do is on each side of this equation, you replace E of X and P with estimators for those things. Now remember, E of X is the mean expected value of X. We also in chapter 3 and 4 called it a moment, a first moment. E of X squared is called the second moment. E of X cubed is called the third moment. That's why this is called the method of moments. Replace E of X with a statistical moment. E of X gets replaced with X bar. That's a statistical moment. I haven't called it a moment before to this point. But moment is sort of a word that is synonymous with average in statistics, a certain kind of average, certain kind of expected value. Realize that these are not the same thing. E of X is a number, X bar is a statistic. They're not the same thing. P is a number, P hat is a statistic. I replace P with P hat. These equations don't mean the same thing. This is an equality of numbers. This is an equality of random variables. But they're related to each other. And what you do now with the method of moments is you solve that equation for the unknown statistic that you're trying to estimate or that you're trying to find. So P hat is going to be X bar over 20. In this context, for this problem, you could also write X bar as the sum of the Xi's. I goes from 1 to 5 divided by 5. Because remember, M, the number of the sample size, I guess there's 5. Yes, there's 5 samples. Each row of pines is a sample. That's what X bar is for this problem. If it were a different problem with a different sample size, then we'd have a different formula there. If M were 7, we'd have a 7 there and a 7 there. And in the end, when you divide by 5 and then divide by 20, that's the same as dividing by 100. So we also could write the formula like this. And then you can look at data. In each of the data here, each Xi is the observed number of trees that survived in each row. So each Xi is actually counting the total number of trees that survive in each row. I didn't really emphasize that like I should have until just now. And so you really are adding up how many survive out of 100 total trees in the end. Okay. It's a weird method, but read the examples. There's a second example that's harder. You'll start to get it.